Welcome to Unit 6 of COMP526. This is a unit on compression, on how to represent text with using less space. The outline is as follows. I will give you some context what this is all about, and we will look at a plethora of different compression methods. I will also motivate why this is necessarily the way to approach compression. And we'll talk about many of these, some of which you've apparently seen already, but I'm sure some of the more advanced ones you have not seen yet, or not all of you have seen. It's also another unit where I can bring you very close to the state of the art in research and definitely close to the methods that are used in practice for compression. So even though we start with very basic things, again, putting the basic steps together in the right way gives you the state-of-the-art methods for compression of, say, English language text, and that's a really nice and beautiful outcome of this unit. So let's get started with what compression is about. If you remember the last couple of weeks and before the Easter break, we were talking about strings and string matching already. And these units were really about how to work with strings if they are represented in a convenient format for us. In particular, we talked about extensively how to find substring, how to find matches of a substring that are not exact matches, but approximate. We talked about other related questions, finding repeated parts, finding all sorts of more esoteric features that people have identified, for example, in computational biology to be of interest. And we solved all these problems in one way or another. But what we started with was assuming a string is given as an array of characters, where I can, in constant time, jump to the character at position 1,500,437. In the next two units, we will switch gears a little bit and look at how we can store and transmit strings. In a sense, this is something that underlies the previous units as well, because we assumed strings before to have characters from some alphabet, but really to work with them, we have to store them in the binary memory of our computers. So it's inevitable to talk about how to encode characters at one point or another. And that is part of this unit as well. But then the more important and more interesting aspects come into play when we try to store strings with the least amount of space possible. And in the unit 8, we will also look at how to transmit strings over noisy channels when there's a communication channel that introduces bit flips and little mistakes. How can we still guarantee reliable transmission with very high probability? That will be, in a sense, the opposite of compression. You don't try to use as little space, but you try to make it as robust as possible. But they turn out to use similar ideas and similar techniques. The methods are related in a way, so that's why we discuss them together. But for this unit, we will focus on how to represent strings with little space. Now let me come to the question I already asked. So here's our nice tag cloud of compression methods. I see Huffman coding, Huffman encoding, Huffman codes are well known. A couple of people also voted LZW, the Lempel-Sif-Welch algorithm that we will discuss in detail probably tomorrow. And a couple of others. So I see there's Lossless, LZR, I'm not even sure I know this one. Yeah, DES is, I think, some encryption methods. Yep. And zip, of course, I was expecting many people to report zip or variants of it. So any type of data compression method, the ones that you use for sending data across the internet, chances are that it's actually zipped on the way somewhere in between. So these are really everywhere, these methods. They're applied ubiquitously. Okay, and some more esoteric ones as well. Codecs for video and audio. Cool. Thanks for participating in that one. So you know what these things are. You have seen a couple of examples, at least many of you. And in case you have submitted none, you will see plenty of them in this module. I want to start with a bit of terminology. So this is just that we talk about the same things with the same names. I'm not sure if this terminology is very universally agreed upon in the literature and on the web, but for this module, we'll try to stick to it. We always start with a source text, and that will be denoted by S. That comes from some alphabet sigma S, and it can be of any length. That's the thing we start with, and we want to store or transmit it. And what we transform it into is the coded text, denoted by capital C, and it comes from another alphabet, sigma C. And often we actually use the binary alphabet because we want to represent or transmit things on a computer. But the terminology here or the methods are not necessarily tied to this choice, even though it's the most prominent one. We will the process of taking the source and transforming it into the coded text, that will be called encoding. And the process of going the other way around, back to the source from the coded text, that would be called decoding. I think the terms are probably self-explanatory, but I want to be very clear. And also I will use these letters S and C without explaining on the slides what they stand for. These will always be source text and coded text. Another thing, we will focus on text because that's convenient and it's a nice formalism, but it can actually be anything. In particular, the same terminology can well be applied to multimedia files, to audio, to video, to pictures, to time series of certain measurements, to, I don't know, 3D data from, make up whatever you want. At the end of the day, if you want to represent something in a computer, you have to convert it to the sequential binary format that computers speak. And so it's ultimately a text at one stage or another. You always need to represent things as a text. So in a sense, this is no restriction. It's just starting at a lower level for certain types of data. The other big remark here is there's two types of compression really that differ substantially, fundamentally in the techniques and in the ideas that they use. And this is the question about lossy versus lossless compression. The first one, lossy compression, is only representing the source text approximately. So you start with some source text, you encode it, and then you can go back to something that's similar to S in a certain sense, but you will not ever get back the exact same S. So this is what you usually use for multimedia data, where as a human or even as an AI, you're usually not even able to tell the difference between those two if the compression has high enough quality. So why bother recreating the exact same source text if all you want is a nice representation of that picture you took with your phone, right? So this is for media files where they are always just an approximation of whatever they capture, are only an approximation of reality. Also, the compression can be just an approximation of the exact source text. The main thing here is you need a good notion of what it means to be approximately the same. And this depends a lot on what you want. You will remember MP3 for representing audio. Well, what do you mean? You will know MP3 for representing audio. And that one is actually a very, very crude approximation of the original audio file. If you look at all the frequency bands, it just happens to be that our ears, the human way to receive and process audio, means that for us, the MP3 coded version and the original source text version sound the same or very much the same. But this might not be true for other animals, for example. So this is a very specific thing, and usually you have to come up with a specific idea for every type of media. Lossless compression, on the other hand, always has to come up with the exact source text as it was originally, so you go back to the exact same source text bit by bit. And in this unit, we will focus entirely on lossless compression algorithms, because these can be universally applied to all kinds of data. You can always apply the lossless compression without losing anything that's in the name. And it can often be combined with lossy compression in a meaningful way. And the second reason is the techniques for lossless compression are very much algorithmic combinatorial in the realm of this module, whereas lossy compression would have to talk a lot more about perception, about brains, about specific types of data. Now, we've seen there's different types of compression. What makes a good compression? What makes a good encoding scheme? So a combination of encoding and decoding algorithms. That entirely depends on the application. Typical criteria can be how fast can I encode and decode? How efficient are my algorithms for doing that? Can I tolerate certain mistakes or noise in the transmission? Totally different thing is how about the security? Is it easy to decode if I maybe not want this to be possible by someone else? Do I require certain keys to enable decompression or decoding? Integrity, is it possible for me to detect whether some malicious third party has made changes to the coded text? Another thing. And lastly, that's what we will focus on, the size of the coded text. How long is the coded text? Can I compress it below the size of the original text? So as I said, we'll focus on the size of the text in this module almost entirely. So we try to find encoding schemes that minimize the size of the coded text, and this is generally called data compression. And there's a specific quality metric, a simple number that that people usually use to compare compression. And this is just dividing the length of the compressed text. So this is length of the coded text divided by the length of the source text. Oh, it crashed again. That is annoying. I don't know what the problem is today with this. So almost there again. Okay, we're back. So the compression ratio, the method of the main measure to compare how good a data compression works, is taking the coded length and dividing it by the source length. And that gives you a number. Now, if the coded text uses a binary alphabet, then the size of this alphabet is 2, log of that size is 1, So in that case, you can just write it number of letters, number of bits in the coded text divided by the length of the source text. You might wonder, why do we have this log of the size of the alphabet factor here? We'll come back to this indeed, but there's a simple argument behind this. Whenever you want to represent something from a set of n different outcomes, you need log n bits to represent that. If n is a power of 2, this works out nicely. So if you have 16 different symbols to represent, you can do that with 4 bits. For something like 20 different letters, you would need actually 5 bits because you cannot do it with 4.5. Well, arguably. Sometimes you can in a specific way, but let's not get into this discussion here. For computing the compression ratio, we just assume that there is such a fractional bit representation for the letters. So we just take log of the size of the alphabet, ignoring the fact that this might be a fractional number and we might not be able to easily represent this in an array. But for computing the compression ratio, we still use it like that. And the compression ratio is nice because it has this intuitive meaning. If it's below 1, we've successfully compressed the text. We've found a smaller representation. The coded text is smaller than the source text. If it's exactly 1, then we achieved nothing. We're just as space efficient afterwards as before. And if it's bigger than 1, we actually made the coded text longer. And unfortunately, yes, that happens. We'll come back to that. Before we come back to that, I want to discuss the limits of algorithmic compression, of lossless compression. I want you to look at this image, which is maybe something you've seen before. Is this image compressible? The answer is tricky because on the one hand, it looks like a very complex shape. It sure is a complex shape. I don't know if I can zoom in here a bit more to show this better. You see that this is, well, you might know this, it is a fractal, and you can zoom in the original representation, you can zoom in indefinitely. In this pixel image that I created from it, you can only zoom in to a certain point. It is definitely a very complex shape and seems to have complexity in it. However, and that means if you store this as a PNG image, which is a format for storing pixel images that uses lossless compression, if you do that, it won't really compress very well. But knowing where this image comes from, knowing that it is a fractal, and in fact it's the Mandelbrot set, knowing this, we know there's a very small mathematical formula that tells you exactly what is the value at each pixel. It's basically computing a certain value and mapping it to a color. So we can generate this picture out of nothing with a very small program. Just specify the parameters, what's the viewpoint, what's the color map, and what's the formula. So in a sense, this program should be a valid compression of this image, right? And this is the idea behind Kolmogorov complexity. It says the coded text can actually be any program that outputs the source text. So it's say a Java program or a Python program, and you have print statements that output the source text. This is not so esoteric as it might seem at first. If you remember self-extracting archives, that was a big thing when when there were not so good tools and internet was not so widely available. It was convenient if you used some more esoteric compression format to actually not just create a zip file, but a self-extracting zip file that contains the program to extract itself. Yeah, Windows installers are similar to this still. So this is the idea in Kolmogorov complexity. The coded text is an encoding for a program that tells you how to compute the source text. And then the Kolmogorov complexity of a string is the length of the smallest program that generates that source text. That sounds like a very sensible foundational definition of compression. If you don't, this is the least restricted version you can think of, because a program can really be anything. But it has a problem, and that is that finding such a smallest program is one of these uncomputable problems. And uncomputable here means provably there is no algorithm that solves this problem. It's mathematically proven that it's not possible to write a program that solves this task reliably. And that is on any type of computer that we can build. So this is a very strong impossibility result. We've talked about impossibility results before. We had a lower bound for sorting, for comparison-based sorting. We've talked about lower bounds in other contexts very briefly, that sometimes in computer science you can make very strong mathematically rigorous statements about certain things that are not possible. And this is a strong thing that sets us off from the natural sciences in many instances. And this is another such example. It's impossible, fundamentally impossible, to write a program that finds the smallest program that generates a certain source text. But that also means there's no optimal encoding for this Kolmogorov complexity. It's not possible to write a compression scheme, a compression algorithm that does this for all inputs. That's a very discouraging result, but it also means, on the positive side, for you as starting computer scientists, it's also sometimes called the full employment theorem. It means, at least for compression and for other problems, you will always need to be inventive and creative to get efficient algorithms. Okay, so much for these limits. So what can we do? What is this inventive? What can we do? What can the creative methods look like? From what I will show you in this unit, you will see lossless compression exploits certain types of redundancies in the source text. And there's fundamentally two different types of redundancies that people were successful in exploiting. The first one is when some characters are very infrequently used in a certain text, they only occur very rarely, then we should spend more bits on those because they don't happen so often. And on the other hand, make the codes for the characters that are very frequent shorter because we use them more often. And that's a substantial boost for many applications. Well, the prime examples of this type are Huffman codes, for those of you who've seen that already. The second type of redundancies, which is a more modern version, are repetitive parts in the text. So there's a certain text somewhere at the beginning of the file, and much later, potentially, there's a fraction, a piece of the file that looks, of the source text that looks almost the same. And that will be these repetitive texts. That will also be something we look at. That's what Lempel-Ziff methods are used for, but we'll see some more sophisticated ones as well. All right. I'll stop with the introduction with a piece of warning. As you will see in the tutorials, there's no such thing as a free lunch in compression. It's again another proven impossibility result is you cannot possibly compress everything. It's not possible to find a compression method that always works, and in a very strong sense so. So again, we'll have to focus on methods that are efficient, not like the uncomputable Kolmogorov complexity, but also we'll have to focus on methods that work often. We cannot possibly guarantee something like they always work. But for the type of data that arises in many applications, they've proven very effective. And so for this module, this is what we will focus on.